How's it going, everybody out there in pre-cal world? Mr. Pike coming to you. In this video, we're going to be talking about rational functions. Essentially, all that a rational function is, if you remember from day one, we had the function x to the negative first power. That was 1 over x. We graphed this function like that-ish, something like that. Right? You saw this in Algebra 2 as well. I know, because it's teaching Algebra 2. Anyways, rational function. As long as we have some variable in our denominator, we will have a rational function, most likely. So it could be some polynomial in the numerator, some polynomial in the denominator that are being divided by each other. That will create different types of graphs. Vertical asymptotes is something we'll have to think about. That is when we have something divided by 0. So for this function right here, this 1 over x, our vertical asymptote would be at x equals 0, because if we had x equal to 0, that's not possible. We can't divide by 0, so that would be a vertical asymptote, and you can see by your parent graph that you have memorized and you've been tested on, we have an asymptote. It's getting closer and closer to 0. Our horizontal asymptote has some rules applied to it. We'll get more into these as we go through some problems. But if the denominator on top is higher, oh no, I got this backwards. I hope you didn't copy this. Junk, absolute junk. I'm sorry. You can throw stuff at me later. I'm so sorry. If the numerator, so essentially what we're looking at here is the exponents. So if x to the n is less than x to the m, where n is less than m, so essentially this is called bottom heavy. So essentially the exponents in our denominator, or on the bottom, are higher than our exponents in the numerator. We will have y equals 0 as a horizontal asymptote. If they are the same, we will take the coefficients of those terms. If it is greater in our numerator, there will not be a horizontal asymptote. We will have something called an oblique asymptote, which we'll get into in a little bit. But for now, you guys, hopefully, even if you don't, this is no big deal, but we'll have some handout like this. I'm going to look at number 1 on that worksheet. X-intercept, y-intercept is still going to be the same as you've always done throughout your schooling. And x-intercept, remember, is when we have some x value and y is 0. Y-intercept is we have 0 for x and some y value. We'll get to the rest of this in a little bit. So x-intercept, remember, you can make y equal to 0, 6 over x minus 3. To solve that equation, you're going to have to multiply by x minus 3 on both sides. That makes 1. X minus 3 times 0 is 0, so you have 0 equals 6. We get a not true statement. Remember, if you get something that's not true, that just means there is no solution, which tells us in this case there is no x-intercept, so there are none. For y-intercepts, you can make the y part 0. So we can say f of 0 is 6 over 0 minus 3. 6 divided by negative 3 is negative 2. So we have a y-intercept at 0, negative 2. I can put that on the graph at 0, negative 2. Remember, you guys can pause and rewind this video. You can hear me say something again, so don't feel like you have to slow down or something like that. Sorry, I'm not going to slow down. I'm going to try to go fast. Anyways, stop talking. So our vertical asymptote, if we take our denominator would be 0 when x minus 3 is equal to 0. Well, that would mean our vertical asymptote is when x equals 3. So when x is 3, I can draw a vertical asymptote. That's pretty bad. Just do the best you can. Horizontal. So in the denominator, we have x to the first. In the numerator, we do not have an x. Going back to our rules. So that would be this case right here. Our numerator is less than our denominator, so this is bottom heavy. If it's bottom heavy, y equals 0 is our horizontal asymptote, and we can have an asymptote. You can't really see it because it's super black. We have an asymptote when y equals 0. Domain range, all that stuff we'll get to in a little bit. So for your graph, we have a point on this side. We're going to get closer to our asymptote as we go and closer to our asymptote as we go. Every now and then graphs will cross our horizontal asymptote, but since we don't have any x-intercepts, we know for sure it's not crossing over our asymptote, so we can just get closer to it as we go. So now we don't know what's going on over here. Sometimes they will be on top, Sometimes they will be below. So we need to figure out what's going on there. Well, we know 4 is an x value that's over here. So if I substitute 4 into my equation, you could have chosen 5, 6, 7, 8, 9, 10. You could have chosen any of those. But if I chose 4, I would have 6 over 4 minus 3, which is 6 divided by 1, which is just 6. So that means I have the point 4. 1, 2, 3, 4, 5, 6. I know it's going to get closer to my asymptote as I'm going, and closer to my asymptote as I go in that direction as well. So there's our graph. So now for the domain, remember that's all the possible x values we have. We have everything except for our vertical asymptote right here. So we can do everything between negative infinity and 3, and 3 to infinity. Range, everything except for our up and down. Except for anything that we cannot have up and down. So we don't have anything when y is 0, so we go around 0, so negative infinity to 0, and 0 to infinity, somewhere in there. For whole, I will tell you there is none. I will inform you when we get to that point, and I will let you know what it is. For end behavior on this one, still as end behavior as x approaches, I'll write this down here. As x approaches negative infinity, what do our y values approach? And as x approaches infinity, what do our y values approach in that direction? The end behavior relates to the horizontal or oblique asymptote. By definition, sorry I didn't write that on your sheet paper definition thing here. Words, why can I not speak? Use words. Oh my gosh. This tells you the end behavior. Always and forever, the horizontal asymptote represents what the end behavior of our function is. And you can see that this is getting closer to your horizontal asymptote as it goes to the left forever, and it's getting closer to your horizontal asymptote as far as it goes to the right. So in both directions, we're getting closer to our horizontal asymptote, which is 0 in this case, and it's getting closer and closer, which we can see from the image that it is getting closer and closer to 0 in both directions. All right, this next part, behavior at each point of discontinuity. This is the removable, the infinite, or the jump discontinuity that we have been talking about. So in this case, I see that we have an infinite discontinuity. That infinite discontinuity is happening when x equals 3. So what we are looking for here is as x approaches 3 from the left, what is our y value approaching? And as x approaches 3 from the right, what is our y value approaching? So again, I know I just wrote that, I didn't really talk about it, but this means as x approaches 3 from the negative side, so from the negative side would be from the negative direction, or from this side, going in the positive direction. So from the negative direction, as we get closer and closer and closer to 3, our y values, as we get infinitely close to 3, they're going down forever to negative infinity. You have to have this notation here that tells us that we are approaching x from the left-hand side. The other side would be just the opposite, as x is approaching 3 from the positive direction. So x is approaching 3 from the positive. So we're coming from the positive, from infinitely positive, and we're approaching 3 from that side. So from the right-hand side, approaching 3, my function is going up and up and up and up and up forever to infinity and beyond. Right? It's going up forever. So I'm going to infinity. All right, that's that one. Let's look at another one. I hope you liked my song. All right, so x-intercept, y-intercept, same sort of deal. Put in 0 for y, put in 0 for x, and solve. I'm going to do that really quick so I'm not wasting too much of your time. So x-intercept, I put in 0 for y, I multiplied by x minus 4 on both sides, so that would divide to make 1 right there. 0 times x minus 4 is 0, so I'm left with x equals 0, which tells us we have the x-intercept of 0, 0. For y-intercept, substitute in 0 for x, so f of 0 is 0 over 0 minus 4. 0 divided by negative 4 should just be 0, so I also have 0, 0 for that, so I can put that point on my graph. Now for vertical asymptote, again, it's when your denominator would be equal to 0, so when x minus 4 would be equal to 0, well, that's when our x value would be 4, is when that would be 0, so I will have a vertical asymptote at Shabadoo. All right, now horizontal asymptote. Again, we got to look at the powers. So we have x to the first and x to the first. Going back to your rules, when the powers are the same, we are going to take the coefficients of them. So if our powers are the same, I look at the coefficients. This is 1 divided by 1 because the coefficients are 1 over 1. So y equals 1 is our horizontal asymptote. All right. We have domain range. Again, we can say domain without even looking at our graphs. We know it'll be everything but our vertical asymptote. And range, we can say everything except our horizontal asymptote. Pole, again, I will let you know when we get there. And behavior is going to approach your horizontal asymptote every time, or your oblique, but we haven't had an oblique yet. So we are approaching 1 in both directions. For the discontinuity, we will have it at 4, so I'll go ahead and just fill this in. So 4 from the left and 4 from the right. We want to know what the y values are approaching. All right, so now for our graph. All right, closer to our asymptotes. Now over here, we need to figure out what's going on. So say choose like 5 or 6 or 7 or 8 or 9 or something. But if I choose 5, f of 5 is 5 over 5 minus 4, which is 5. So 1, 2, 3, 4, 5. Thank you, thank you, thank you. All right, we have a graph like that. That's going to get closer to our asymptotes. So now as we are approaching 4 from the left-hand side, so 4 from the left-hand side, my graph is going down and down and down and down. So I'm going to negative infinity. As we are approaching 4 from the right-hand side, we are going up and up and up and up as we infinitely close to 4, so we are going to infinity in that direction. Cool, that was a lot faster. All right, and this one I'm not actually going to graph it with you guys. Don't worry about the graphing part of it. It looks kind of weird. But I do want to talk to you real quick about this part, our horizontal or oblique asymptote. Because notice, again, in the horizontal and oblique asymptote, you care about the highest exponents. Here, our highest exponent at the top and our numerator is 2. The highest one in the denominator is 1. So when that happens, going back to our rules again, if the power on top is greater, there's no horizontal, but an oblique asymptote exists. To find that oblique asymptote, again, to find the oblique asymptote, because this has an oblique, because the power on on top is greater, we have an oblique. To find it, we do the division that we see. So we see 2x squared minus x minus 1 divided by x minus 4. So I can do synthetic since I'm dividing by a linear function. So I have 2, negative 1, carry down the 2, 8, 7, 28, 27, and I ignore the remainder. The remainder is negligible because as it goes to infinity, it'll become a really, really small fraction, so we kind of just ignore it. So this would be 2x plus 7 left. It's an asymptote, so it needs to be a line. So what this means is that you would graph it just like you would graph the linear function 2x plus 7. So 1, 2, 3, 4, 5, 6, 7, up 2 over 1. And we would have an oblique asymptote that is a line. It would look something like that, with it being more straight. We would also have our vertical at 4. So this is why we're not graphing this one, because it goes like off the paper. And it would have a little curve up there, and it would have a big curve down here. But again, we're not graphing it. So all this oblique asymptote does is it just makes an asymptote that is a line in this case. It could be a quadratic function, it could be a cubic function, a quartic function, any type of function, as long as the powers are greater in your numerator. That's all you're looking for to have an oblique asymptote. I'll talk to you real quick about number 8 and our horizontal asymptote here. Again, the powers are the same. We have x to the first and x to the first, so don't forget you're taking your coefficients. So 4 divided by negative 2 would give us a horizontal at y equals negative 2. All right, moving on. Moving on up. Maybe that's too old for you guys, I don't know. So now looking at number 12. This one, I will tell you, will have a hole. A hole will exist when we're able to divide something out of our function. So here, notice we have a quadratic in our numerator and in our denominator. So the first thing to do, because sometimes weird things happen, so I will tell you, anytime you have a quadratic, it is a very, 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 very good idea, and usually pretty important, that we factor both of them out. Because notice in this one, when we factor that out, we have x minus 3 divided by x minus 3. Well, that makes 1. Whenever you get rid of a factor, we're getting rid of x minus 3, right, and we're still left with x plus 3 over x plus 1. That's fine. Whenever you get rid of this factor, our whole, the x part of our whole, is the solution of that factor. So the solution of x minus 3 is just 3. In order to find out what the ordered pair is that the point actually is for the whole, you can put 3 into our simplified function. So we'd have 3 plus 3 is 6 over 3 plus 1 is 4. 6 divided by 4 is 3 halves. So we would have the point 3 halves for our whole. That's just our removable discontinuity. Let me get the rest of this stuff on our paper real quick that we need from this. Actually, I'll just walk you guys through it. X-intercept, we will have -3, 0. Y-intercept, we will have 0, 3. Vertical asymptote, we have -1. Just use your simplified function from these points on. Our horizontal, we have 1 over 1, so we have a horizontal at y equals 1. So let me throw all this on the graph real quick. All right, so there's all that on the graph. And then our whole at 3 halves, so 1, 2, 3. 3 halves is 1.5, so about right there, I'm going to have a whole, or an open circle. This one's closed in, that's my x-intercept, I just didn't close it in very well. Or sorry, my y-intercept. So now we will get closer and closer to our asymptote, and closer to our asymptote. Same thing in this direction, closer and closer, and closer and closer. Cool. All right, for your domain now, we have to include everything except for the x values we cannot have. So we cannot have -1. We also cannot have 3 because we have a hole there. So we're going to have kind of 3 parts to our domain. So -infinity to -1, and then between -1 and 3, and then from 3 to infinity. Range, same sort of deal. We have -infinity to 1, and then 1 to our whole, which is 3 halves, and then 3 halves to infinity. In behavior, same as going to 1 in both directions, so I won't worry about that for right now. Behavior at each discontinuity. We have our infinite discontinuity at -1, so I can say as x approaches -1 from the left, and x approaches -1 from the right, what f of x does, or our y values. So it looks like it's from the left it's going down forever, from the right it's going up. So from the left it's -infinity, from the right it's infinity. Now we also have a discontinuity right here when x is 3. So we're approaching this whole. Well, coming from this direction, it's getting closer and closer to the y value that the whole is, which is 3 halves. And coming from this direction, it's also getting closer and closer to the y value, which is 3 halves. So in both directions, as x approaches 3 from the left and 3 from the right, our y value is approaching 3 over 2. All right, moving on. We got one more. All right, I'll try to run through this as fast as possible. Thank you guys for being patient in this video. Hopefully you guys have gotten a lot of good information from this. So again, we have a quadratic in the numerator. I will factor that. The bottom will stay the same, which means I will have a vertical asymptote at -2. I will have 2 x-intercepts at 3 and -3. That's fine. My y-intercept will be 0, -9 halves. Horizontal oblique, it will be an oblique because notice we have our power higher on top. So when I do my division, make sure you please remember, notice there's not an x here. So make sure you have 1, 0, and then -9. So we can carry down the 1, -2, -2. The rest doesn't even matter. So we have y equals x minus 2. All right, so now I'll throw that all on the graph real quick. All right, and there's everything on my graph. So again, don't get freaked out by this oblique. It's going to get closer and closer to our asymptotes as we go out in either direction. So it's going to be looking like that. On this side, I have a point here where it's getting closer to our asymptote and closer to our asymptote in either direction. So then for domain, again, it's everything except for your vertical asymptote and any discontinuities that we have. For range, notice this part goes down forever. This part also goes up forever. Likewise, in this part of our rational function, it goes up forever and it's going down forever without any break. So we have everything from -infinity to infinity. There is no whole because I did not get rid of a factor, my in behavior. So now, as x approaches -infinity, y is approaching something. And as x approaches infinity, y may be approaching something else. So remember, I said our oops, sorry, I didn't circle that. Our end behavior is the horizontal or oblique asymptote. So notice the oblique asymptote is the linear function y equals x minus 2. If I were to just graph x minus 2 by itself, it would look like that. So really, if I just think about what our graph is here, as x is approaching negative infinity, this graph is going to negative infinity, just like this one is. So that should be negative infinity there. As the asymptote goes to infinity, it is also going to, sorry, as x goes to infinity, my graph is also going to infinity, so it's going to infinity in that direction. Your discontinuity is going to be negative 2 from the left and right, so x approaches negative 2 from the left, x approaches negative 2 from the right, f of x approaches, yes, yes, oh yes. So if I'm approaching negative 2 from the left, negative 2 from the left, I'm getting closer and closer to negative 2 from the left-hand side. It's going up forever to infinity. Negative 2 from the right, it's going down forever to negative infinity. All right, hopefully this video has been helpful. As always, we are always in our rooms for you guys. We love you guys. Can't wait to answer your guys' questions because that's what we're here for. We can teach this all day, but answering questions is the really fun part. At least that's what I enjoy. All right, instead of drawing monkeys, it's not as much fun. That's why my monkeys get worse as they go through time. That's a monkey! Bye-bye!